Last time we looked at a sequence of independent events and we looked at the probability of getting a specific outcome, meaning heads, 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 or tails, 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 tails. This time, I don't want to look at specifically head, 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 or tail, tail, tail. I want to look at the number of successes we have in our multiple trials or events. So let's stick with flipping a coin 3 times because it's easy. And we're going to talk not about the probability of head, 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 or tail, tail, tail. We're going to talk about how many successes did we get. And let's call heads a success. What's the probability in these 3 flips that we got no successes, or the probability we got 1 success, or 2 successes, or all 3 of them were successes. Now, last time we did this by multiplying the probabilities together. This time we're going to look at a slightly different way. We're going to look at the sample space. If we list all of the possible outcomes in a situation, we call that the sample space. And I've got that here. And all heads, all tails, or head, head, tail, head, etc. There are 8 possible outcomes for this situation. That's our sample space. Each one of them are equally likely. And remember the definition of probability. If you have a sample space where all outcomes are equally likely, all you have to do is count the ones that you consider successes and divide that by the total number there are. So if we're talking about this being our success, that there were no heads, there's only one of these situations that we consider to be a success. And that would be 1 out of our 8. And we already know that, right? Because the probability of all 3 being tails would be 1/2 times 1/2 times 1/2, which is 1/8. Same thing for 3 heads. We have one of these outcomes we consider to be a success, fit that description, out of the total of 8. Now this is where this is a little bit more useful than what we did last time. If we want the probability that there's 1 success out of the 3 of these, there's 3 different ways that could happen. These 3 outcomes each have just 1 head. So 3 of our equally likely outcomes out of the 8 outcomes is the probability that if we flip a coin 3 times, we'll get heads exactly once. And the probability we'll get heads exactly twice is going to be these 3. So 3 out of 8 there also. So if you've got a sample space where all outcomes are equally likely, then the probability of whatever situation is just how many of those outcomes fit that description divided by how many outcomes there are. Now we'll look at a couple additional little details here. One is that if you've got the probability of each of these situations, all the possible situations should add up to 1, and they do. If you add 1 plus 3 plus 3 plus 1, you get 8, so that would be 8 out of 8. And that's an important thing. If you look at all the possible outcomes, the probabilities should add up to 1. That's the whole. And that can be useful when you think about something like this. The probability of at least 1 head. Okay, that's not the probability of any specific number, just saying there's got to be at least 1. Well, I can look at that a couple different ways. They'll work out the same, of course. I could look at this as how many of these have at least 1 head in the outcome. And that would be all of them except for that one. So 7 out of 8. And for this particular situation, that's really easy to do because I'm just looking at a simple list of 8 things. When we get to a more complicated situation, it might not be as simple as that. So I want to suggest a different strategy here, which is if you want to know the probability that you get at least 1 success in this situation, that you start with 1 and subtract the probability that there will be 0 successes. Right? The probability that you get at least 1 and the probability of getting none, well, that adds up to all of them, right? That covers all bases. So all of those together should add up to 1. So all you have to do is start with 1 and take away the probability that there are no successes. We already calculated that up here. That's the 1 in 8. That's the same 1 in 8 there. So we have 1 minus 1/8, which gives us exactly the same thing. But suppose we had a list here of 1,000 different possibilities that didn't all have equal probabilities. Well, I would not want to say the probability of at least one and go through and calculate all of those different probabilities and add them together. I'd much rather say, well, it's going to be 1 minus the probability that there were no successes, boom, done. And we will run into that idea again when we get to discrete probability distributions. We got one more probability topic to get through, and then we'll do the real fun stuff.